How many have seen a Blue Gene device? And why is the Blue Gene like this? Cooling. Why is the Blue Gene small? The Blue Gene's small. Well, I mean, depends what you mean by small, but if it's in a computer room, it's small because it has to reduce latency. And it's the idea is, how for $20 million can I reduce latency and control heat? Sort of a large data cloud is a sort of a different animal. There, I want to. These containers are from pictures of the containers in the Microsoft data center in Chicago. These are they stack the containers 2 and 3 high in the data center. They have a traditional data center with racks, and they have a portion of the data. The data center is partitioned into things with racks and things with containers. And there, the goal is to maximize the amount of data, match it with compute, and sort of keep the cost as low as possible. You want to control the cost. So instead of minimizing sort of heat in a constraint with reducing latency, here I want to reduce cost. Same thing in Elastic Clouds. That's another data center. I sort of want to minimize the cost to provide a virtualized infrastructure, a machine image on demand at lowest possible cost. So these are all related to types of optimization problems. This is my slant of something you've probably seen 17 times. I'll do it very quickly, but if I had to explain in one slide why I get excited every morning and really am happy to doing big data science, it's because of this. These are real numbers. I computed them themselves. As people who've worked with me, they probably know that they're wrong because I tend to compute things wrong the first time or two. But I went to the published literature. I went to books, and I tried to figure out every time a new device was introduced what the scale-up was prior to the introduction of that device. So that's a picture, I think, as best as I can tell, of Galileo's telescope or something like that. And it was introduced in 1609 and introduced a whole new science, but it only gave us 30x what we could get from the visual eye. So that science came by giving us a device that gave us a 30x factor. The microscope was introduced about 60 years later, and it gave us a magnifying power of about 250x, and it gave us a whole new science. One of the first computers I ever used is pictured there. It was the Cray. I think Jeffrey will know these numbers better than I, but when I tried to sort of do quickly in a couple of hours, figure out what increase you got over other large machines prior to the Cray, it's 10 to 100x. That was around 1976, and it began what you might think of simulation science. So when I do back-of-the-envelope computations by looking at, say, Google's 10K and trying to understand how big their data centers are, how much computing power, I think you could convince yourself there's probably a factor of 100 to 1,000 there. But I don't want to be wrong, so I brought it down by a factor of 10. And so I think if you fill up a data center with scientific data and then allow software to scale out and do analysis services at the level of the data center, then it's at least a factor of 10 of 100. So from this viewpoint, we should have a new data science that's ever been as exciting as the other simulation science and the observational science that came from the telescope and microscope. So, I think this, to me, if we can't get something as exciting, it just means we're lazier, we're not as smart as the scientists a number of years ago. So if you feel you're not as lazy and are just as smart as other scientists, I think the future is for us to create some kind of data science that's just as exciting, which exists when you can fill a data center full of scientific data, fill multiple data centers of scientific data, and then try to figure out what new kinds of science we can do. So that's pretty much my talk. I have 180 more slides because I'm going to talk for a few more. But to me, this is the take-home message. Now you should go home and figure out how to do this. So a lot of the way I look at data these days is pretty simple. There's small data. Small data fits in memory. There's medium-sized data. It's like the three bears. Medium-sized data fits in a database. And then there's big data. Big data is too big to fit in a database. So from that viewpoint, it's always interesting to look at traditional database technology and compare it to, say, something like Hadoop Cloud or Google Cloud or something like that. So this is where I get a factor of 1,000. These numbers are, to first order, a database gets hard to manage after a couple hundred terabytes, but I can certainly manage 100 petabytes using data centers. I certainly can't do full SQL queries, but I could do a lot of powerful stuff. Think about what happens every time you use Google. Databases are optimized for safe writes. These kind of things we're talking about here are optimized for very efficient reads, scans especially. The consistency model for databases, I won't go into, is called ACID. Does anyone know the trendy name for the consistency model for sort of large-scale clouds? It's called BASE, and I'll tell you a little later why it's called BASE. Parallelism in databases can be done, but it's tricky. At some level, these kind of large-scale things are about parallel computing frameworks, and the scale is a rack versus a data center. I was going to talk a little bit about that, but I'm not. So how many people own Knuth's book? You don't? Well, then probably my next bit of advice is you should not listen to the rest of the talk, and you should go to eBay or Amazon or Abe and buy Knuth, and you'll probably learn more from reading Knuth than you will from listening to me. Well, I won't look at the screen to see who's leaving, but that's probably a better use of your time than listening to me. So those are 3 volumes. There's new books coming out. So the challenge I want to give you is, on the right is a data center. So Knuth's book was, at some level, at a very high level, it's about how we can program computers. Now, it's a very broad notion of a computer. The computer can have tape, the computer can have memory, can have external memory. It's about programming a computer. And the question is, how much of Knuth applies when I program a data center, and how much new things are required when I program at the scale of a data center. So I think that's a great topic for a PhD. And then the question is, if I want to make it simple, how do I chop up science into different disciplines so that I can have simple ways to program at the scale of a data center that are easy for people to use. So let me just try to whet your appetite. I talked a little bit about building a data center, but think of a data center as a bunch of containers, and then your budget determines how many containers. A container, say, costs $1 to $2 million, and I just stack them up to fill a warehouse. And then these days, you're going to get ruggedized containers, and you just plug them to cooling, and you plug them to maybe water and electricity, and you leave them in parking lots. So the first question you might ask is, I know what an operating system is for a computer. I know a little bit about how we build operating systems for HPC devices, but how do I build an operating system for a data center? What does that operating system need to do, and how do I do that? So that's one question. And so, if I think of a workstation having 5 virtual machines, then maybe a data center has 50,000 or 100,000 or more virtual machines. And what is the core operating system required to do that? For people who looked at clouds, there's this sort of provision sometimes from infrastructure to platform. And so, one way to think of these things is whether you have a single or many instances, and whether I'm just bringing up a single instances, I'm bringing up services on multiple instruments like a platform, or I'm having core services that will scale out to a data center. So I think of the race right now with Microsoft and Cisco and VMware and others, is how do I build a data operating system for a data center. And so that means I need to have virtualization at different layers. I need to be able to have security and restart and all that. But how do I do that? And so there's this sort of provision where you see sort of the Amazon style, which allows you to bring up instances and gives you simple queue service and some database services. But if I have 1,000 of these and I want to manage virtual networks and I want to move these, that's really not part of the Amazon style. Whereas the platform provided by Azure allows you to do certain things and not think sort of at the level of these VMs. In fact, you can't even do a VM. And so this is one way to organize that. So now the question is, we talked about the operating system. Let's think about how we program it. So one way to think of it is Google had they had software engineers, and they wanted them to say if you wanted to experiment a variant of the core things you do when you have web documents, inverted indexes, word counts, and so on. What framework could I give a brand new software engineer so with the least amount of code they could do something non-trivial with an inverted index or a word count or something like that? So that's the problem. I want a framework so that if I take a new software engineer, then in the shortest time and the least code, they could do something. So the way I think of this is, we have a lecture room, we have a distributed lecture room. Think of each chair as a disk. Think each disk is half full. In each half full disk, fill it with Word documents. Now, what's the simplest framework I can provide to compute an inverted index? So the Word documents are strings. Each web page contains a bag of words. For each word, I want to find all web pages anywhere in this room, from any disk in this room, that that web page contains that word. It's called an inverted index. How do I do that? Well, the easiest way to do that is to write a system that assume all the disks are half full. The first thing I do is take each web page on each disk in parallel, and I tell each disk to take each web page and extract all the words, and then on each local disk I'm going to say divide it up into, if there are 100 chairs, I'm going to divide it up into 100 little buckets on that web, and I'm going to take each word, I'm going to hash it to one of those buckets. So in phase one, I'm going to extract the words and hash on the local disk to 100 buckets. Phase two, I'm going to do a pull simultaneously from each local disk, and I'm going to each disk is going to pull from all the other local disks all similar buckets. And so each word in the end will get on one machine, and it will have sort of a list of all the pages that came from there, and that's sort of the reduce operation. And I want it on text. I want it to be easy. This sort of the shuffle and the sort is what the system does. All you define is your reduce. All you define is your map, and you're done. So that's MapReduce. You heard some talks about Twister. That's a sort of an iterative version of that with some twists that you heard earlier this week. You heard a little bit about how Microsoft thinks about what's the framework to do this. How do I program over a bunch of disks? What we decided to do, we sort of did at the same time and didn't know about some of this work. We said the simplest thing that what I want is many computer scientists, many scientists think in terms of a function. So I want to take a room full of disks, I want to take a warehouse full of disks, and I want to apply a user-defined function in a couple lines of code to the entire warehouse full of disks. So that's what Sector does. We'll describe that model. Some people, their entire lives of some people and some scientists are dictated by SQL. They can never get too far from SQL, and so you can ask, what's the simplest way I could do SQL or quasi-SQL-like things over a warehouse of disks? And they're so-called NoSQL databases that